your hat so we can see the end. We were at the point yesterday or the other day where we talked about weight and friction. Those are the last two things we had gotten to. Shh. So we spoke about an example with some of the forces. We did that already. But we want to make sure that we understand what this is here. So again, this is the weight of an object. Mass times gravity. I always take the mass times 9.81 to see what you get for the weight. Now remember, the weight itself is a function of the planet it's on. Because the weight could be either more or less than what it is on Earth, depending on the gravitational pull on that other planet. So if you look at the weight of an object on the moon, because the moon's gravitational pull is 1/6 of the Earth, you weigh approximately 1/6 of what you weigh on the Earth. What's constant though, always?
Mass.
On that planet it is. Mass. If I'm here and then suddenly tomorrow I'm on the moon, my mass is the same. It hasn't changed. The mass is the amount of matter that makes up my body.
How'd you get that fast?
I'm pretty crazy like that. It's over here. Instantaneous transmission. Like Goku.
Oh.
From Dragon Ball Z.
Oh,
I thought
So, if I want to remember this, the only thing that varies in this formula is g, depending on what I'm on. If I'm on Earth, on the moon, on Saturn, on Jupiter, wherever I'm at. The mass of an object is always constant. So weight is a function of gravity. Weight is a function of gravity. Obviously, it's a function of mass also, but what I'm saying is it can change based on gravity. The mass of an object doesn't change unless it's a new object altogether, and then you have just two different objects. I guess, yeah, a mass of an object could change if you just cut it in half, or if you cut like the leg of a chair you cut off, obviously you're cutting off a lot of mass. But we're assuming that the object isn't changing there. The last formula, Ff equals mu Fn. This is the force of friction, mu Fn. Fn is the normal force. So what does this tell me about the force of friction? It's directly related to the normal force. Now mu is like constant of proportionality. Mu is like your direct variation constant. You know in math class?
It's like mu with an S and mu.
Correct. What did they stand for? You remember?
It's like a coefficient of mu.
Yeah, the coefficient of friction. Now S and K, what was the difference?
Static and kinetic.
Static and kinetic. If it's stationary, use mu S. If it's sliding already, use mu K.
So you have to break S.
Exactly. And it might say you have to overcome static friction, right? So it says what force would be needed to get it moving. That'd be using mu S. And then if it says what force is needed to keep it moving, mu K. Now Fn, if you recall, think about what Fn was. Fn is the force that is directly perpendicular to the surface that an object rests on. It's a reaction force. Right now, Fn is pushing back up on this iPad directly up, or vertically. Okay, it's pushing up on that iPad. If I were to, let's use this as an example, I'm using this pencil because it has a longer grip. If I were to take this pencil and slide it across the table, I'm overcoming friction, right? Now, if I were to take the same pencil and push down on it, and then try and slide it, the same force. Like I would look at like the example, I'm pushing very lightly on this, right? Very light. And do the same thing, I'll push down a little bit, and then try and do it. I'm going to push with the same light force. It won't move. It's not even budging. Why?
It's more normal force.
Yeah, I push down harder. More normal force indicates more friction. So when I'm pushing down, what does the table do? It pushes back up. If I push down harder, the table pushes up harder. So as a result, if I push down with more force, it's really just increasing the normal force. And since the normal force is related to the frictional force, if I push down harder, I'm actually increasing friction. That's why if you do this, right, when I want to erase the board, do I go like this? No, it's not working. It didn't work. You know, like I would never do that. What would I do?
You can't hide the truth.
I just can't hide the truth. What would I do though, honestly? Push. When I push, it increases friction. And as long as I push hard enough, this object stays between my finger and the wall. So the minute I let go, I'm decreasing the normal force. Okay?
Yeah, it's the same.
You always say washroom, don't you? Yeah.
Yeah, but
Change it up today.
we threatened to punch her when she said that. Because all freshman year it was always bathroom, and then she came back with Ethiopian and it was like, oh, washroom.
It's called a wash closet in other countries.
Yeah, I know, but like.
Yeah, but this is WC. This is America.
What cloth?
I'll bet
I didn't know this was America. Oh man, all right, never mind. Now we're good. All right, next slide. So in this chapter, we talked about work and energy. Work and energy were both measurements, listen please, were both measurements of quantities that were measured in joules. The work done on an object was force times distance times cosine theta. Force is Newton, distance is meter, so Newton times meter became a joule. So the work done on an object, so if I push on this iPad with a certain force for a certain distance, I'm doing work on the object. That work is kinetic energy is changing to. That's the work kinetic energy theorem on the third line there. So the first thing that we started with again was work. You need a force, you need a distance applied, and an angle at which you're pushing with. The second part was kinetic energy. Kinetic energy has to do with motion. Thus, there's a velocity as a parameter in this. Okay, so if you have motion, you have kinetic energy always. Any motion at all. Even rotational motion. We haven't gone over that, but there's rotational kinetic energy. If something is just revolving. Spin a top, you know, like a top. If you spin a top, it keeps spinning because of its rotational inertia, but it has rotational kinetic energy also. This work kinetic energy theorem is assuming there's no change in height. Jot that down, right? If there's change in height, we're going to use the conservation of energy theory, which tells us this. It's not even on here. It's just something that we know.
Is it on the formula sheet?
Yes. What?
It's not on the formula sheet?
MEI equals MEF?
Yeah.
I don't think so. You can look. Open it up to see. Look at the most updated one. I don't think it is. If it's not on here, it probably isn't. Or else I screwed up on this sheet. Maybe it should be on here. I don't think I put it on there, though, did I?
What's that relation you wrote?
MEI equals MEF?
Well, it's just combining the.
Conservation of energy?
I don't think you put it in line, it's more like you have to.
It's theory.
Yeah, like if you're changing.
The whole concept is that the energy you start with is the energy you end with. So you might have potential and kinetic in the beginning and only kinetic at the end. So the energy is just changing as a result of the motion. It's not on there, right? Okay. And I don't think it was. Now, the force that's used in this formula, let's take a look back up at work before we go on to potential energy. This force here, what force is it? What force could it be? Applied force, good. What else could it be? Gravity. Work done by gravity, work done by an applied force. What else does work? Not normal. Friction. Friction does what kind of work? Yeah, so, louder. Negative work. The reasoning, if you remember, is that motion is point which way motion is for now, hypothetically. Which way? Okay, so we're moving this way. Which way is friction? What's the angle? What's the cosine of 180? Negative 1. Cosine of 180 degrees is negative 1. Friction is always opposite motion, so it's always going to be 180 for that one, okay? Always. So we plug in 180 for theta there, and we'd get negative 1 as a result. The next formula is potential energy. Potential energy is a function of what? Specifically, what is it a function of? That was ugly. Height. Very good. Change in elevation. That's what we're working with here. M is the mass of the object. Every object has a mass. G is gravity. On Earth, you have gravity. It's the height that actually matters for this. So if an object starts on the desk, slides, and ends on the desk, is there a change in potential energy?
No.
No, because there's no change in height. So that's why I was saying for the word kinetic energy theorem above it, if there's no change in height, all you have to use is the word kinetic energy theorem. If there's a change in height, you have to then incorporate potential energy, which means you should probably use the mechanical energy conservation theory. And that, again, tells us on the far right what we have over here. I'll rewrite it over here again. MEI equals MEF. And remember, this simply means all of the energies that it has in the beginning. So let's think about a sample scenario. An object is on the top of a building, and the object falls off the edge of the building or is kicked off with a given force. So it's kicked off with a certain velocity from the top of a building. What kinds of energy does it have if it's kicked off with velocity and it's at the top of a building? Anthony?
Kinetic during the middle.
Kinetic? Oh, it's kicked off with a velocity, I'm telling you. There's initial velocity. Yeah, kinetic and potential at the start. Because it's kicked off with velocity, given the velocity, assume, right, on the problem, you're given the velocity. Because you're given VI, you know it has kinetic energy initially. Because it's at the top of a building, it's got potential energy initially. Now, on the way down, tell me what's happening on the way down.
As it's falling, it's losing potential energy, it's losing height.
Good.
And as it hits the ground, it goes, potential energy zero, it about transfers into kinetic energy.
Yes. So on the way down, it loses potential energy because it's losing height. But doesn't it pick up velocity when something falls until it reaches what we call terminal velocity? Something where you have a balance of forces actually. But the concept is that the potential energy at the top is all transferred into kinetic as it falls further and further down. So a problem like this, you would write, okay, well I've got kinetic energy at the top to start because it's kicked off the building. I've got potential energy to start because it's got some height. And then at the end, when it hits the ground, it's all kinetic energy at the end. So I would utilize this formula right here. Well, where does that formula come from? It comes from right here. Okay, conservation. That's why conservation is not given, because it changes based on the parameters of the problem. Conservation of energy should be a theory that you understand, and then applying it is what you see in this box right here. That's one example. What if I was launching something from a spring on the ground? Well, then it's got PES, potential energy in the spring that's stored, 1/2 kx squared. So that would go in the beginning. And then maybe it's got nothing else in the beginning. It's got no height and no velocity. It's just in a spring. The spring releases it and it launches it. And you want to find out, well, when it gets to 20 meters, what's the velocity? Well, at 20 meters, it now has potential energy and kinetic energy. So you could say, for an example like that. So again, an object is launched from the ground, from a spring. What is the velocity at 20 meters height? Well, at the ground, it's got potential energy in the spring. When it's at 20 meters in height, it's got potential energy and kinetic energy. And again, this is like the initial on the left-hand side again. It's in the spring and it's all loaded up. The spring releases it. When it gets to 20 meters in the air, it's got velocity and it's got height. So it has both of these types of energy when it's 20 meters in the air.
It can only have a spring energy really initially, right?
Correct. Unless it lands on like a trampoline and stuff, but that would be way more complex because it would land and then it would shoot off again, and then it would, it would be a different kind of problem. We've always done them with the spring is initially at rest, or the object's initially at rest in the spring. And S, you could think of as stored energy also, if you'd like to. At PES, right, that could be spring energy or stored energy. Either way you want to think about that is fine. P equals W over T. Is this P pressure? We've been looking at pressure for a while now. Is this what pressure is?
No.
What is this? Power. Power is the rate at which work is done. Rate tells me that I need to divide by time. Power is the rate at which work is done. So work divided by time is power. Okay, you should know that. Now, what are my units of power? My units are watts. The W is a unit, not to be confused with this W, which is work. This W is a variable for work. T is a variable for time. But when I get this, I'll have joules for work, seconds for time. Joules per second is a watt. Okay, is a watt. And then finally, the last possible formula. If you have a constant force applied to something for a constant velocity, or a given velocity, I should say, constant though, you could also calculate the power. Just an alternative to the previous one. So this chapter was on work and energy and then power at the end. Okay, that was chapter 5. Chapter 6 went into momentum, impulse, and collisions. So let's take a look at that. The first thing we learned in chapter 6 was that everything that is moving has momentum. Momentum can be thought of similarly to kinetic energy. Kinetic energy is the study of the energy of an object due to its motion. Momentum has to do with its motion also, but it's not really energy. It's this weird concept. Remember, there were no units for this? The units were just kilograms, meters per second. Kilograms coming from mass, right here. Meters per second coming from velocity. So if I have the mass and the velocity of an object, I can calculate its momentum. I'm probably not going to give you something that easy. It's probably going to be something where you have a collision. And that comes in from the last two equations. Okay, or the second one also, and I'll go over that in a moment. But let's look at the last two here that I just boxed in. The first of the two, what happens physically? Tell me, what do you know about the first equation? What would have to happen for you to use this equation? What would have to physically happen in the collision for you to use that equation there? What would have to happen? Chris?
Two objects would collide at velocity and they stay together.
That's the second
They
one.
separate.
The second one, look, Chris. The second one, you see the masses are added together in the second one? Okay, so Chris gave us the second one where they stick together. Yeah. Exactly. They collide, they separate, and they separate with their own velocities. The first one, meaning the one where they separate, is called elastic. It may not be perfectly elastic, but we assume it's perfectly elastic. The second one is called inelastic. In the first case, we're going to see that the energy is conserved. There's conservation of energy in this case right here. So the energy before the collision should equal the energy after the collision. Whereas in the second case, because of the fusion of these two objects, some energy has to go into that. So we lose some energy in the second case there. And we lose some energy in that second case right there. Yeah, lose energy in inelastic, which is the second one at the bottom there, okay? It's usually, well, you don't lose it. It's used up. So like if two objects collided fast enough, they might heat up when they actually collide and fuse together, and that energy that's lost goes into the heat that is needed to fuse them together. So you're not losing energy, it's just transferring into something else. How about this? I jump off of a ledge and land at a shopping cart and I start going down the street in a shopping cart. Ridiculous, I know. But say it happens. It's inelastic because I'm stuck together. Where's the energy loss? When I land in the shopping cart, the energy that like actually hurts, like the physical amount of like when you slam your knee, that's actually energy. That's the energy loss that is going into. It's a theoretical idea. You don't know where it really physically goes, but it goes into something. It transfers into something else, dependent upon the scenario. How about this formula? Delta P equals F times T. Ooh, what would we call that? I'm going to shut this one off. It's getting cold now. What would we call that? Delta P equals F times T. There's a name for this. There's a name for this. Sam, do you remember? Yeah, good. The impulse theory, or the momentum impulse theory. Very good. It has to do with impulse. What the heck is impulse? Because I guarantee you, if I asked you all right now to write a definition of impulse, maybe one or two would get it in the whole class. Most people don't even know what impulse is. What's impulse?
I forget the exact word, but it's like a, it's kind of like it's a value of the, I thought I knew it.
How about it? Kinetic energy is not, it's nothing to do with energy. I mean, it's related to energy because you're changing velocity, but it's not energy. That's inertia, right?
The distance. Can you show up, Ariel? Thank you.
The energy created something
Again, not energy though. A lot of you have the right ideas and stuff, but it's definitely not energy.
heat. It's the impulse of by an object.
Impulse is the impulse function. That's it. Shimon, help us out.
Well, I mean, according to the thing, is it the change in momentum, like in a situation,
So, give an example.
All right, so if you jump off,
Okay.
so a gymnast, doing flips, and the reason why there's a mat is because by increasing the time of impact, it decreases the amount of force.
So the impulse itself is Ft. That's the impulse. This is called momentum impulse theory because look, change in momentum equals impulse. Write these down, please. This is change in momentum over here. This is physically impulse. Impulse is F times T. And exactly what Shaban said is the application we want to think about. This was the egg drop. The egg drop was this one formula. That's it. The egg drop was literally this formula. If you can increase the time it takes for that egg to slow down, you decrease the amount of force on the egg, thus it doesn't break. Katie Eisler's was, I think, the top one as far as like design and ingenuity. Hers was a bunch of different like straws and different things that when it landed actually like bent out and bent back. It absorbed the shock. It took a lot of time for it to slow down. It didn't hit the ground and stop instantly. The object, you actually, the teachers loved to see, they saw this. when we dropped it from the 5th floor, it actually landed and like actually bent so much that it touched the ground and then bent back up. Have you ever seen a basketball compress when it hits the ground? It did exactly that. So if you increase the time period of contact, you're decreasing the force. That's why when you catch an egg in like that egg toss on those block parties in the summer, you do this. You cradle the egg. Because what are you doing? Instead of it hitting my hand and contacting for like 0.1, sorry. You gotta wake up. Woo! Scared you. And maybe it's like 0.1 seconds, right, of contact. Well, if I do this, it's like a full second of contact. So I increase the time by 10, decreasing the force by 10. So if the force of contact or the force on the impact would have been 50 newtons, now it's only 5 newtons because I've done this. You follow what I'm saying? So the increase in time decreases the force felt, but the whole idea is that where does this come from? A change in momentum. Change means final minus initial. So the formula that is very useful to jot down, that is not really on here, even though it is what this becomes. So let's write what this becomes. This formula, if you think about it, is really final momentum minus initial momentum. And momentum is mv. So this is really mvf minus mvi equals ft. That's the formula you probably want to use. But you have to recognize that delta P means final minus initial, and that P final is mvf, and P initial is mvi. This is not density. This is not pressure. Okay, lowercase p is momentum. Density is not lowercase p. Density is that symbol called rho, that loop symbol. It's a little bit different. I know it looks the same, but you should know based on the context, mv means you're looking at momentum. P equals mv. If you're talking about density, density equals mass over volume. So don't confuse this. You don't have to write this down. But look, top right. This is density equals mass over volume. It looks very similar to this formula right over here, where it says momentum equals mass times velocity. That's velocity. That's capital V for volume. You see how these are very similar? Okay, a lot of you mix this up, just so you know. I know you're all like saying, oh yeah, I get this. But on the last test, when we had fluids, many people use this formula instead of this formula. Okay, they're very different things. So that's it for chapter 6, the idea of collisions. That's, I think, if I recall correctly, I think that's where, we did up to the midterm there. So that's semester 1. Semester 2 on is what we've been doing. I'm going to try to go through semester 2 stuff a little bit faster because it should be more recent, right? It should be stuff that you've done recently. So let's start with this chapter. In this chapter, what kind of motion did we look at?
Circular motion.
Circular motion. Circular motion. So an object moving in some sort of a circular way. Wheels, planets, cars around racetracks, an object on a cord, like a lanyard spinning, the bucket example, merry-go-rounds, anything moving in a circle, which is so much stuff, involves circular motion. Wheels, even believe it or not, this filament that loads into the 3D printers comes off of an object that's moving in circular motion. So there's actually some tension in that cord. Like, so much stuff involves circular motion. What did we look at? We looked at these two main things. We looked at this concept that there's got to be something that's keeping it in circular motion. And that's called centripetal acceleration. Now, with centripetal acceleration, we also came up with the following. We said if we want to find the centripetal force, we take mass times acceleration. And since acceleration here is Vt squared over r, that's what we end up getting for centripetal force. That was another formula that was useful, that was not on the formula sheet, but it comes directly from Newton's laws. Newton's laws tell us F equals ma. Well, instead of a, I'm just plugging in the value of whatever a is, which is this. This is what a is. And when it's in circular motion, you take the tangential speed, square it over the radius. So this is the acceleration from this part. Just plug it in. You have F equals ma. So if you want to know the centripetal force acting on an object moving in circular motion, utilize that formula. We did this and we talked about at one point thresholds. For example, a person swinging on a vine. The vine has a certain threshold. It will snap after a certain force is exerted on it. So you would calculate the tension in it to see if it would snap or not. We did it in the lab where you guys were spinning the rubber stopper and you had that little string you had to spin to get the radius to work. So we did a lot with this. Mathematically, we didn't do too much. It wasn't that difficult, the problems. I'd recommend look at your problem set problems for this for sure. The next formula relates our universal gravitational law to masses. This is different than the formula for gravity we learned earlier. The one we learned earlier was this. Fg equals mg. The mass of the object times gravity, and we were done. This was assuming we were on a given planet, on the surface of that planet, and we knew little g on that planet. But what if we're looking at the gravitational pull between a planet and an asteroid? Or the gravitational pull between two planets, or a planet and the sun? Well, then we have two masses involved. We always have two masses involved. Even this formula, believe it or not, there's two masses involved. The one is the mass of you, the other is the mass of Earth. Well, where's the mass of Earth? It's not here. It's embedded in g. If I look at this formula and I take a look here, there's little g right there. That's little g. M2 is the mass of the object. So if you actually calculate the gravitational constant, which is on your formula sheet, times the mass of the Earth over the radius of the Earth squared, you'll get 9.81. So that circle part in blue that I just circled there, that's where little g actually comes from. It comes from this ratio right here. And then M2 would be the mass of the object. That's where this formula comes from. But the idea here is that we could calculate the force of gravity between any two objects. Any two objects exhibit gravity on one another. Now, again, does my gravitational pull on your pen actually pull it toward me? If it did, that'd be really cool. I'd be like a Jedi, right? The Force. Use the Force. That's the whole idea. But clearly that doesn't exist, right? So I can't do that, unfortunately.
Wow.
I know. Right? I've ruined it all for you. So the gravitational pull of the Earth exceeds my gravitational pull so much that it's insignificant. And it doesn't actually cause any change. All right. What else in this section did we talk about? Where did we talk about Kepler's laws? I feel like we got Kepler's laws in there somewhere too. Was it 7e? Did I create like an extra section?
Yeah.
I did. I got to add that here. Whoops. All right, I got to remember to add another section here. We talked about Kepler's laws. And Kepler had 3 laws we talked about. We had 3 laws. They were not Newton's 3 laws, right? They're different 3 laws. Kepler's 3 laws had to do with planetary motion. It had to do with like the area swept out is the same. Another one had to do with the ratio of the period squared to the distance cubed is a constant for all planets. Another one said that the sun is one of the focal points and the planet moves in an elliptical orbit. So if I were you for Kepler's laws, I would study the theoretical part of them. It's not going to be a heavy math problem at all on that. If it would be anything, it would be a very simple math problem for that kind of stuff. Okay, it's mainly theoretical.
I was just wondering if you can answer this because we had a problem on that test that was finding the perimeter of an ellipse. You had to.
It's probably a form. There's got to be a formula for it.
Yeah, that's what I.
You mean the actual length of the curved path of an ellipse?
Yeah.
Like what is the? It's not circumference technically, but like what is it you're saying?
No, we just wanted the equation.
Yeah, okay. It's the ellipse
He
equation.
wasn't asking for like,
It's always x squared over something plus y squared over something equals something. I don't think it was the distance around it because you would probably use calculus to get that actually. You would definitely. Maybe he said if a rectangle was around it, what would the perimeter of that be?
We never learned
I don't think you would do perimeter in his class. All right, chapter 12. Chapter 12 had to do with the beginning of waves. We started learning about sound waves and different types of waves and harmonic motion and Hooke's law and things that vibrate on certain frequencies. We talked about like springs. We talked about a pendulum. Pendulum that goes back and forth is the same thing as a spring going back and forth. They're analogous to one another. So this whole section was about springs, harmonic motion, and waves. We had a lot of formulas here. Let's take a look at them. We started with Hooke's law. F equals negative kx. This is the force in the spring, and that equals negative kx. Why is it negative? Anybody remember? Why is it always negative? And?
Because it, like, apply force to spring depends. So
Which way does the spring want to go? So I pull on a spring, right? Where does the spring want to go? To the opposite direction. Okay, the spring force is always opposite the direction that your x is. So this x value will end up being some sort of negative, or it'll cancel out in the end. But that's where the negative really comes from. The spring force is called a restoring force, meaning it wants to restore the object to its original shape. Gravity is a restoring force also, but that returns like a pendulum to the bottom of its path. Right? What keeps a pendulum from doing this, or what stops it? It makes it do this. Friction stops it, but gravity is what causes it to stop eventually at the bottom there. It's a restoring force. X is the stretch in the spring. What is K? What is K? Ash? The strength of the spring. The spring's, we could say, constant, the spring's rigidity, the spring's stiffness. Any of these words are fine, but it's the strength of the spring. Higher K, stronger spring. So a spring in your pen that you click on, that little clicker on your pen, that spring is a very low K value. It's very weak. The springs on your cars that keep your cars from doing this after you hit a little bump, those springs are extremely, extremely rigid. They have a very high K value. Now, please don't start thinking to yourself, well, if the spring is longer, it's more K, or if it's wider, it's more K. Those are not necessarily directly related. Okay, it depends on the material of the spring, the number of coils, there's a lot of stuff. So you don't have to know what actually goes into K, but know that K means the strength of the spring. Higher K, harder to stretch or compress the spring. What do you think? Your bed mattress, before you had what is it called now? Tempur-Pedic, right? And memory foam? You had springs in the bed. Would those have been a high K value or a low K value? Think about it, logically. I know what reasoning. Your answer actually could be either, but the reasoning is what's important. Give me a reasoning behind your answer too.
just relative to what size you're comparing it to. If you haven't really.
That's a great answer. It depends on what I'm comparing it to. You're right. But if you were to have to classify it as strong or weak, what would you classify it and why? What do you think? Or medium, you could say. It depends on what you think.
I'd say medium just because the smallest spring I know is like that, and the largest one is for a car. So it's
Okay. But I want reasoning as like aesthetics of a person. Help them out.
I'd say it'd be a strong spring supporting your, like also talking comfort. I always hear like the spring goes out. It's not a good thing. It means the spring broke or something in the bed, which is bad because it's not supporting your body. It's going to get out to whatever way. So I'd say it'd be a strong spring that's supporting yourself.
Okay, Francis?
It also feels strange because spring, because I don't think you have one spring in bed that'd be very uncomfortable. So if you have more than one spring, you'll have even distribution of weight. So, and if you have spring that's too hard, it would terribly uncomfortable for the person. And you kind of just like bounce off the bed.
If the spring is too strong, you hit it, you shoot off, okay?
Mine's kind of see this practices. It's like there's a lot of them, but they each distribute your weight. So it's not like all your weights are on one screen. It's like it's divided into all.
Yeah, it's like that example with pressure. We talked about laying on a bed of nails, right? You're laying on a bed of springs. Now, theoretically, the answer could have been anything. Because you could have just said, if I want a firm mattress, stronger springs. If you want a soft mattress, weaker springs. That's really what soft and firm mattresses are before you had Tempur-Pedic. That's why I was saying whatever you want to answer with, but the application is what matters, okay? So if you want a strong or a firm mattress, you probably have stronger springs. A soft mattress would be weaker springs. And then Gabe said in the middle, because Gabe just wanted to choose the middle because it was more chance of getting it right, I think, right? In the middle, right? So it could be any of those things, right?
Actually, with me being less wrong.
Exactly. It may not be right, but it's less wrong. All right, these two formulas are what? What does that T-looking symbol mean?
Period.
Period. The time it takes for a cycle to occur. If we don't know what that means, you should jot that down. Period is the time it takes for one cycle to occur. Hey, look at that. You guys learned trig. You learned about your sine waves and cosine waves. So, trig.
Oh yeah, I learned.
Thank you for That's so funny.
So yeah, you guys learned in trig about sine and cosine waves and how the oscillatory motion works. Well, that's what you're using there. So the period is the length of that segment. Go to Sam and Nick, go to 201. Okay, 201.
I didn't take the test.
Their math test they had to make up. Mr. Hall asked if they could take a nap. Yeah, take a break, guys. Take a break.